Okay, well, hello everybody. Hopefully you're staying warm and safe. We're going to go ahead and get started. I've started recording the session. So as you can see, what I've got here is just a short problem set for us to work together. I'm not going to do all of these. I'll just do some of them to demonstrate. And then the ones at the end are actually review for the earlier topics in the semester. So I'll just leave you to do those on your own as well. But the problems that I'll demonstrate have to do with the key topics from week 6, lesson 2. And so I'll go ahead and get straight into that. And if I do something stupid, or if you have any questions, or if you need me to go over something again, feel free to either type it up in the chat box or just take yourself off mute and bring it up. So here we go. So question number 1, I'll go ahead and start that one. Oops. Hopefully technology will cooperate with me today, as it often does not, but here we go. So, okay. So this one is about the properties of enantiomers. This is revisiting something we talked about several weeks ago, the idea that one unique thing about chiral compounds is that they have this property where they will rotate plane polarized light. Okay. And each stereoisomer will do that differently. And particularly enantiomers will do it just the opposite. So if one enantiomer rotates plane polarized light in a clockwise direction, 20 degrees, the other enantiomer, the mirror image, will do just the opposite. It will rotate it counterclockwise 20 degrees. So that would be like a minus 20 degrees, okay? But with enantiomers, that's the only physical property that is different. All the other physical properties are the same. The boiling point, the melting point, the solubility, the vapor pressure. Okay, that's not necessarily true of diastereomers. Diastereomers, as we've seen in the lessons, can have different boiling points and melting points because that 3D arrangement, those unique 3D arrangements, will lead to slightly different intermolecular forces, which is what dictates the melting point and boiling point and the solubility and things like that. So to answer this question, we can kind of, remind ourselves about all those other topics as well. So which of the following properties differs for two enantiomers? The only thing that would be different would be the way in which they interact with plane polarized light. Okay, so that's number 1. All right, so let's look at number 2. Okay, so one of those chiral compounds is carbone, all right? And you can have two enantiomers of that, what they've called here the R version and the S version. And there is a, sort of a textbook or table tabulated value that's important with regard to these, and that's called specific rotation. And so the R version happens to have a specific rotation of negative 61 degrees. Okay. And assuming we've got the same conditions, standardized conditions, what would be the specific rotation of the S carbone? Well, remember that's what I said. It's just the opposite. So it's still going to be 61 degrees, but it's in the other direction. So this time I'm going to say a plus 61 degrees. Okay. It's not the same. It's just the opposite. So plus 61 degrees. So just remember that's the property or the relationship between that property between enantiomers. Okay. All right. Very good on that one. So I'm going to demonstrate, I'm going to skip number 3. I'm going to let you guys work on that one. I'll turn on these questions at the end of our session. But for now, I'll skip number 3 and I'll move on to number 4. All right, so let's take a look at this. So consider a molecule with a specific rotation, and that's the sort of the symbol of the specific rotation, that Greek letter alpha in the brackets. And here's the value, negative 17.25 degrees. What are the following properties could be predicted from this data? Okay, so what can you tell if you know that the specific rotation is negative 17.25 degrees? Okay, well, one thing you can't know is whether it's S or R. And by the way, you can't, you can know whether it's dextrorotatory or levorotatory, whether it's D or L, because that's what the sign tells you. Okay, positive would be D, the dextrorotatory. Negative would be L, the levorotatory. But that's not what we're being, led to here in these answer choices A and B, because remember there is no firm connection between D and L and S and R. That's all experimentally determined. So I don't want to pick A or B. We can't tell looking at this number if it's an S configuration or if it's R configuration. The other thing you can't tell is how many chiral centers are present. It could be sort of, a conglomeration of multiple chiral centers that leads to this specific rotation. Okay, that they are not inherently connected. Okay. One thing that you can know is that it's not a mixture of isomers. So that's why I don't want to choose this one. This one in answer choice D is saying that it contains a mixture of isomers. Well, that can't be true. Otherwise, it wouldn't be a specific rotation. That term, specific rotation, is for a single isomer. A different isomer would have a different and its own specific rotation. So I don't want to choose D because I can't know. And matter of fact, I know that it is not a mixture of isomers. That's the whole meaning behind a specific rotation. Okay, but what I can know, and this is what I choose, is that it must not be the mesoform. Remember that the mesoform is optically inactive because the mesoform has that internal plane of symmetry. It kind of cancels out the optical activity you would get otherwise from the chiral centers because they cancel each other out sort of within the molecule. If you think about tartaric acid, the mesoform of tartaric acid, that form of tartaric acid where there's that plane of symmetry that cuts the molecule in half, that had an optical activity of 0. Okay. So that's just one of the characteristics of meso compounds. So I know that because this is a non-zero number, that it can't be the mesoform. So that's why I would choose E. All right. Okay, so that was number 4. Um, so now I'm going to go ahead and do number 5. This is a calculational one. This is one of the few calculational topics that we have in Organic 1. And it's not heavy calculations, but it is a little bit calculational. And I want to demonstrate how to do this. And I'm actually going to demonstrate a little bit beyond the solution to this one, just to, again, kind of talk about the full way to calculate the composition of a mixture that has an enantiomeric excess. Okay, so what we're told here is that we have a S-carvone. It's optically active and it has a specific rotation of plus 61.1. Okay, and then we have an observed rotation of 25. Okay, so what we want to do, we have to report as our answer just the enantiomeric excess. But I'm going to take it one step further, and I'm actually going to calculate the full composition of this mixture. Okay, but the answer that we're going to punch in, the answer that we're going to report is kind of a step before that. Okay, so remember that the equation that we're going to use is that this percent of enantiomeric excess is just this. It's the observed divided by the specific rotation. Okay, and then we're just going to multiply that times 100%. So we're just going to substitute in numbers here. So we know that the observed rotation is 25. It says has an observed specific rotation of 25. So that's my numerator, 25.0 degrees. Okay, and I'm told that the specific rotation for this compound happens to be a positive 61.1, okay, degrees. All right, and then I just multiply that times 100%. Okay, well, if you do that, you divide 25 by 61.1, what you get is 40.9%. Okay, so that is, the enantiomeric excess. That's what we want to report as our answer. I'm going to leave that on the screen, but I'm going to go ahead and type that in. Okay, so this would be 40.9. Okay, but this question, I just want to take it a step further and talk about how to get the actual composition of the two isomers of this mixture. All right, it's just another, I did one of these calculations in the lesson itself, but I'll just do another one here now. Okay, so remember that that's the excess. Okay, so the rest of it is a racemic mixture. So I got to figure out how much that happens to be. Well, if there's of course, everything is 100%. So if I start with 100% and I subtract from that the 40.9%, all right, that's the excess. So that comes out to be, let's see, 100 minus 40.9. Let me do that calculation real quick. I thought I had it written down, but I guess I don't. That's okay. So 100 minus 40.9. So that's 59.1. 59.1% is racemic. Okay, and remember what we mean by that. Chicken scratch, racemic. So remember that means that it's 50-50. It's half and half. It's half of one and of one enantiomer and half the other enantiomer. So that means that I just need to divide this by 2, right? So if I just divide 59.1, so if I divide that by 2, then that is 29.55%, we'll say S, and then 29.55% R. Okay, that's what composes the racemic part. But we already said that we have an excess of 40.9% of the S version, right? And how do I know it's the S version? Because it has the positive rotation. Okay, so this is, it's 40.9% enantiomer excess of S carbon. Okay, so I'm just going to add that to my, portion of the racemic that's also XS. So I add to that the 40.9 from the enantiomeric excess. Okay, and if you add those two numbers together, the 29.55 plus the 40.9, what you get is 70.45. So 70.45% S, okay, and then the rest of it, the 29.55% R. So that's the composition of this mixture that gives you the observed rotation of the 25. Okay, if it were a 50-50 mixture all around, if by molecule, it were a 50-50 mixture, it would have an optical activity of 0 because they would cancel each other out. And if it had a fully, if it was fully S, not a single R molecule in the mixture, if it was fully S, it would be plus 61.1, okay? But it's somewhere in between. And so we are able to use the observed, that 25, and the specific, the table value, the 61.1, to do this calculation and figure out the actual composition of this mixture. Okay, so this is the type of calculation I want you to be able to do. Okay, come up with, use the observed rotation and the given specific rotation, including the sign on it. Okay, because what do you think the specific rotation for the R enantiomer would be? So the R enantiomer specific rotation, the table value, would be equal to a negative 61.1 degrees, okay? Because they have that property. If the S is positive 61.1, pure S is positive 61.1, pure R would be a negative 61.1. Okay, so try and put all these concepts together in your mind and get a pretty good proficient understanding of all that. But like I said, really what this question is asking is the first thing that we did. We just wanted to calculate the enantiomeric excess. But my expectation for the test would be do a problem like this to come up with the full composition. Okay. All right, so let's just submit that answer. All right. So that's number 5. So number 6 is a similar kind of question. I'm just going to go ahead and let you do that one. And as I said, number 7, I think the rest of them, 7 through 10, are all review. So 7 and 8 are review about pKa's and strength of acids and which side of the reaction it favors. 9 and 10 are just some naming questions. So what I'm gonna do is I'm gonna click start of all these, and I'm gonna let you guys work on them. We don't have to stay online, of course. If you want to go ahead and log off and work on those, that's fine. I'll hang back for a minute or so just to see if anybody has any questions, since we do have some time left in our Zoom meeting. But I'll shut up for a second, take a drink of water. I'm still hoarse, as you can tell. My throat still is killing me, as you might be able to tell. But if you have any questions, like I said, take yourself off mute or put it in the chat box. Otherwise, if nobody says anything for a minute or so, we'll just go ahead and end the meeting. In case you're wondering, while you're typing, it's kind of to be determined what we're going to do tomorrow. I think I told you my prediction is that we won't have the campus will be closed. I think this is just Dr. Moore's speculation. Campus will be closed Wednesday and Thursday. It just depends on how much snow we get. So just stay tuned. Look for an announcement in Blackboard about what we'll be doing tomorrow. And this will be uploaded, for those, if you have friends that weren't able to log in live, as soon as we're done here, I'm gonna upload the recording to YouTube and put the link in Blackboard as an announcement. Okay, so if you do have a question, feel free to email me. I'll respond as soon as I can. I do have another class. I got to do another Zoom class at 1. But I appreciate everybody logging in. Stay safe, stay warm. Thanks.